everybody. Thank you for coming. I know there is 2 million sessions this afternoon, so thank you for deciding to spend some time with me. We're going to talk about all things Cloud Edge and WebAssembly. How many of you have at least heard or used WebAssembly in the last couple of years? Okay, not too many. So for all the others, no worries. We'll look at what it is, how it relates to Python and many other languages, and all the fun stuff we can do. We'll focus mainly on the server-side stuff. I know WebAssembly is very popular also for browser execution and so on, but as many of you, I care a bit more about the server-side stuff to run WebAssembly. So what's the agenda for today? I'll go into a bit of WebAssembly details. I'll talk about edge computing as well. That's a bit of a plot twist about the session. Maybe you know about the cloud. Edge computing is a little bit of an extension of the cloud, and why did it come to exist, and what does it mean, and how it evolved. So a little bit of history as well. And then a bit of intro about server-side WebAssembly, how the two things can live together and be happy together. And I'll share a bit of a use case about how we're using this stuff at Edgy. I'm Alex. I'm a developer advocate at Edgy. I'm a software engineer. I spent a lot of time in the cloud in the last 10 years at Cloud Academy and then at AWS for 6 years today at Edgy. I also found a very nostalgic picture of a much younger Alex speaking at PyCon 7 in Florence in 2016. So I really wanted to, I'm really happy that now it's in Bologna, which is the city where I live. So happy to be back at PyCon after a few years. So what is edge computing? It means a lot of things. It's an umbrella term, I like to say, depending on the context. So maybe you've heard about edge computing in the context of IoT devices and smart manufacturing. And every time you try to bring computation not to a centralized place, but to many different edge nodes or IoT devices and so on, that's not what we're talking about here today. I want to focus a little bit on the web side of things. I know that many Python developers also work with cloud and web technologies, and we'll focus a bit on what I like to call the CDN-based edge computing, which is a way to run compute logic on top of content delivery networks. The Fastly, the Cloudflare, the CloudFront of the Akamai, and so on. So we'll stick and try to stick close to the web world as a web developer, former web developer myself. And so there are many ways to talk about edge computing. The general idea is, again, to bring computation closer to where it's actually needed. Often it's to an IoT device because the computation needs to happen there, like for computer vision and so on. Today we talk a bit in a bit of a different context. So I don't want to go super far back into the 50s and 60s about the history of the cloud, but it's important to realize that the history of edge computing is kind of an extension of the cloud, and the cloud is kind of an extension of how the internet works. So if you're curious, maybe take a picture. There is a lot of articles and links to dive deeper into the history, the long lost history of the internet. Let's focus a bit more on, you want to take a picture? I'll go back. This is basically how the internet is born, and then it became, very much cloud-based in the last 20 years. Maybe you've heard of, the first cloud provider, AWS, in 2016, launching the first few services, after virtualization became a thing. And then we went from, ordering a server and getting it in-house 5 months later to getting a virtual machines in 2 minutes, right? Like on EC2. And then we went from that to containers. You can spin up tens and hundreds of containers in a matter of a few, maybe 20, 30 seconds. And then we went to serverless, where you can spin up a micro virtual machine in 200 milliseconds. And that's kind of the state of the art for the last 10 years. Why do I want to go through this history? Because another thing that evolved in a similar way in the last 10 years is the world of content delivery networks. So maybe you've heard of CDNs in the context of, you put it in front of your website to protect the backend from DDoS attacks, for caching, for those sort of things, to deliver content and to protect the origin. And some of these companies are as old as Google. Akamai was born in 1998. I think it was the year after or before Google was born. So they've been around for a long time, as old as the internet almost. But these also evolved in the last 5, 6, 7 years introducing what they call like compute at the edge. So for example, in Fastly, you have compute at edge, you have Cloudflare workers on Cloudflare, you have Lambda at edge or CloudFront functions in the AWS world, you have edge workers and Akamai containers in the Akamai world. So the idea that these are not just a little network of hundreds of edge nodes that allow you to cache content and improve performance, but you can actually run your application on top of those edge nodes. It kind of changes things, right? It opens the way to some interesting scenarios. And then as soon as you have compute, you realize, that's not enough. We need storage, we need key value storage, we need databases, we need object storage, we need queues. So if you look at that from this point of view, a CDN today is almost like a cloud provider. They offer what cloud provider used to offer 10, 15 years ago with compute and storage and databases and all these things. So there is this idea that came up, in the last 5-6 years that you can run almost full stack or end-to-end applications directly at the edge without needing a server or an origin or a cloud deployment at all. You usually do, but let's talk about that later. The other pillar of this talk is WebAssembly. Some of you know about it, some of you do not. I think this is one of the most interesting technologies of the last, again, 4, 5, 6 years. It's not very new, but it's also not very popular and adopted yet. I think the cloud and the edge are very interesting in this space. It allows you to do a lot of things like cross-language. So if you are a Python developer, okay, it's interesting, but not in itself. So maybe you want to use a Rust library or a C library or a .NET library or a PHP, maybe not, library. Can I mention other languages at PyCon? Yes. And it's interesting because the main goal of WebAssembly is to have full portability. So I can compile something on this operating system using this language, and then that binary file, that's the output, I can run it on any other operating system, and I don't even know where it originated or what was the source code initially. So it's really interesting, this idea of portability and composability of application at runtime. So for Python, usually you can either build components or you can build a host that runs components. We'll talk about some of the details. But really, for you, maybe you are building the library that somebody else in, I don't know, C or Rust is using the Python library compiled to WebAssembly, for example. There are a lot of cool things we can do, and later we'll look at some use cases as well. But why is this important? How many of you have used Docker in the last 10 years? At least once a year, it's everybody uses Docker for a reason or another. And this is a mandatory quote, very popular in the WebAssembly community. In 2019, this guy is one of the founders of Docker. He said, well, if we had WebAssembly and WASI 10 years ago, we wouldn't have to invent Docker in the first place. That's kind of the, whoa. So it's not just a cool little tool or a cool little technology. It could have been the replacement of Docker if it was a bit earlier. And now there's Docker, so that I think that's why it's not being adopted as fast, because Docker already exists. But there are a lot of people in the community that think that Wasm plus WASI, we'll see what WASI is in a second, have the potential to become, for some use cases, in some scenarios, a good replacement or a good improvement instead of Docker. So not a small deal. So WebAssembly, it's all open source, the specification, the documentation, you can find it online. There is a missing piece if you want to do server-side stuff, which is what we care about today here, which is WASI, okay? So I think WebAssembly became very popular with the idea that you can build with any language and then run it anywhere, for example, in the browser. So there are many projects that allow you to run Python in the browser or to run C and Rust and Go in the browser, and that's super exciting. But if you actually want to run anything on the server, you also have to provide operating system functionalities and interfaces. That's kind of what Docker does, if you think about it, like a standardized interface on top of any operating system, that the host system. And that's what WASI is for WebAssembly. So it's a POSIX-like API that allows you to say, hey, this is WASM module. This is how you call the file system. This is how you call sockets. This is how you call random and clocks and all the things that the operating system provides that you want to re-implement in the application. So these two things together allow you in any language, including Python, to build WebAssembly components. There is a bit of a distinction here. If you know about WebAssembly already, you probably are aware that there is WebAssembly modules, which is the past in a way, and then you have WebAssembly components, which is a bit of the future. It's still in preview, but a lot of people are building with this idea of the component model. So this comes with the idea of composability, where I can build a component in Python and a component in Rust and another component in Go, and blend these three things together based on this WASI interface thing and compose an application like that. Okay, good, interesting use cases there. Maybe not in a single team, but with the idea of reusing shareable components across marketplaces or whatnot is really fascinating. And so what are some of the benefits? Well, why would you want to learn and dive deeper into WebAssembly? First one I mentioned, platform portability. This is pretty crazy if you think about it. I can compile on my MacBook and I give it the binary file to you on Windows and it runs. It's not usually that way, right? Near native performance. This is fascinating for use cases where, like in the browser, where you want to run a Python library or you want to run a C or a Rust executable in a place where it shouldn't, or it's not that easy to do, and achieving really good performance there, like instead of JavaScript or instead of other host languages, is really fascinating. Lightweight and fast initialization is pretty crucial for server-side stuff. If you've used Docker, you know that the artifacts that you end up building could be hundreds of megabytes, right? So a WebAssembly component is usually in the hundreds of kilobytes. That's like many orders of magnitude lighter and easier to move around, easier to deploy and to push and so on. Initialization, similar thing. How long does it take to spin up a virtual machine or a Docker container? Usually it's in the minutes or in the tens of seconds. With WebAssembly, we're talking about hundreds of milliseconds. So more similar to the world of serverless and function as a service and AWS Lambda, those kind of things. So very interesting for some of the use cases you will see later. Secure sandboxing is my favorite. Have you ever had the use case where you need to run somebody else's code? They have no idea who they are. Maybe you don't even know what languages they are using, but they need to give you something and you need to run it in a secure way, making sure they don't do file system tricks or network tricks so you don't become a farm bot or being able to securely run arbitrary, untrusted code is a very tricky problem. And with the sandboxing that WebAssembly provides, it's built in. By default, a component or a WebAssembly module has no access to anything in the operating system. So you give me a component, I know I can run it, and you're not messing with my system. That's pretty cool, and that's one of the way that, for example, we use it at Edgy by telling people, hey, you want to run something at the edge, give me the component, I'm going to run it in my managed service, and I know you can't mess with the rest of the system or the deployments. And multi-language support, I think it's fun, not necessarily because you want to go crazy and build one application with 5 languages and try to merge things together, but there are use cases where maybe a specific library or a specific thing that you need was not built in Python and you still want to use it. If you can compile to WebAssembly, you can import it as a module and run it in your Python app. So it's pretty flexible and useful. Now, there are some cool projects here. Does this work? Yes. There are some cool projects that actually run in the browser. So in the Python world, some of this stuff started existing like in 2018, 2019. There is a very cool project called Pyodide. It was born 4 or 5 years ago in 2020, 2021. It's basically a port of CPython to WebAssembly. So like you basically compile Python to WebAssembly. It was started by Mozilla. Now it also includes a lot of the NumPy and SciPy stuff as well. This also gave life to projects like Jupyter, Jupyter Lite, and being able to run the thing that you run in the browser today, which is actually Python stuff. Well, how would you ever run Python in the browser? This is enabling that. but this is stuff in the browser. If you want to run server-side WebAssembly in Python, you typically do components. And so you need what they call a componentized library or a utility. This is usually stuff built by the Bytecode Alliance, and I'll show you some more resources later about it. But basically what you do is that there is an interface that your component implements. And so first of all, you generate the bindings. There is a lot of code generation stuff in the WebAssembly community. So you say, generate the bindings for the interface that I need to import or export, and then you actually compile with the componentized Py utility, and that becomes a .wasm file. Okay. For Python, I told you that usually WebAssembly components are a few hundred kilobytes. That is true for compiled languages like C, Go, Rust, and so on. For Python, you kind of need the whole standard library, and that's an interpreter. You can't really compile that. So that adds a few tens of megabytes to the story. It's still a couple order of magnitudes less than a 300 megabyte Docker container. But still, it's a bit heavier than the compiled languages, as you can imagine, because you have the entire interpreter bundled within each WASM component. Not optimal, but that's what you need for all the benefits we talked about. And then you also have the opportunity to actually be a host. There's this idea of a host and a guest. A guest is a component. A host is somebody that runs those components. So you have projects like Wasm Time Py, which is the Wasm Time port of for Python, where you can say import that local folder that I generated earlier, and then I create a config, enable caching, create the engine and the store. That's what you need as the host. And then I can simply invoke the function that my component is defining directly there. So there are some limitation in the Wasm Time Py compared to the Wasm Time written in Rust, but nobody stops you from using the Wasm Time written in Rust to import Python components. So it's a bit of a mix and match. Yeah, these are the two projects I mentioned. But there's also a fun little project here. It's called Nuitka. I'm not sure how to pronounce it, but it's basically like a Python+Wasm compiler as well that allows you to be more than 3 times faster than regular CPython in WebAssembly. So it's pretty cool. Different ways, and this phase in the WebAssembly community is a bit earlier. So you see all these different projects doing similar things with different use cases, but it's pretty cool. And what WASI allows you to do is either define your own interfaces and or use some of the default pre-built interfaces that you would expect from an operating system, like the clocks and the file system and the HTTP or TCP sockets, the CLI kind of interface. So these are pre-built, defined by the Bytecode Alliance on GitHub. This is the project that most people use to run and build a host. And most of these tools are built by a nonprofit organization called Bytecode Alliance. So they build, compilers and runtimes and all the tooling, most of the tooling that I talked about so far. There are a lot of global companies that you probably recognize that support this working group and this community. So it's pretty cool. You can join it. It's not super expensive if you want to invest in the community as well. Now, Wasm plus Edge. Let's go back. I presented you Edge computing. I presented you WebAssembly, a little how to get started intro and how it relates to Python. Now, why these two things can live together and what you can do with it. So I think one of the biggest difference, if you're used to cloud or traditional hosting, one of the biggest advantage or difference when it comes to Edge is that it is globally distributed by default, right? So if you deploy a typical Python or server-side application, it runs on one data center or one cloud region or one instance somewhere, right? Whether it's EC2 or container or serverless. But when you deploy an Edge application, you hit deploy, and it's actually deployed to usually 80 to 100 plus Edge locations in a click. Okay, so that's useful to know as a developer that there is some built-in distribution. And also, if you're building for the web, you know that you're already kind of optimizing for latency, because the people visiting their website or that URL is going to hit the closest edge location. So if they are in Australia, they're probably hitting the Sydney POP or point of presence or edge location. Now, there are some resource and performance constraint worth knowing, because it's a bit different from the cloud. You have some limitation as far as how much CPU time you have, how much memory you have, how many lookups or HTTP calls you can do. And typically, you want to be as fast as possible, because what happens typically is that you have the edge application and some kind of origin where the ground truth or the website or the content sits with a database and a server-side application living there. And so your edge application, you don't want it to add 200 milliseconds to every request. The recommended best practice is try to stay within 5 or 10 milliseconds. And what we do at Edgy today, for example, is our Edge application has a P99 of less than 5 milliseconds of latency in addition to every request. So that's not super easy to do. We actually use Rust to achieve that level of performance because of the network and low-level nature of the proxy that we run there. I'll share more later. But then there are some key benefits of WebAssembly that we talked about earlier that are really, really important for edge scenarios. The native performance, again, we want to run as fast as possible at the edge. We cannot sit there for half a second. It needs to be 5, 10 milliseconds kind of speed. The sandboxing for us is incredibly useful because we want to allow third-party components to run on our infrastructure, and that's part of the mission. And then the small size is also very important because often you need to download and run and instantiate these components. And again, you cannot afford to wait seconds. And so downloading 200 megabytes or downloading 20 megabytes or downloading 200 kilobytes is very different when it comes to latency and end-to-end speed. So WebAssembly is really giving us that advantage. So quick case study of what we are actually doing at Edgy. It's a bit of a, I like to say, a strange product because it solves a business problem, but it uses a lot of cool technology that I like to explain. So what we do is that if you have a website today, I lost it. Yeah, if you have a website today, your browsers or mobile device, whatever browser device, is probably overloaded with client-side scripts and JavaScript stuff like analytics and talking to analytic APIs. So what we wanted to solve is to move all that logic from the browser, because it's hard to control. It's blocked by ad blockers. If you don't have cookie acceptance, you really can't run that stuff. We wanted to move all that logic not to the browser, but to not the server, because it's complicated and you cannot have caching, and there are a lot of problems because every server is different, every application is different. So what we do is we run that logic directly at the edge, and we use WebAssembly to enable this idea of first party. I lost it again. Yeah, first party and third party components. Every component implements a specific data collection API or cloud service API. We also built a registry, and that's how we enable first-party and third-party components to exist. And today we support mainly analytics APIs or cloud APIs because that's where the business problem is. But we want to go into, A/B testing and security firewalling and AI inference and a lot more stuff. So it's pretty cool. We built some local development tooling as well, trying to hide some of the WebAssembly complexity, because otherwise, as a developer, you need to learn about all the details. And some of the details are different for each language. So maybe you're a Python developer, the tooling and the complexity is different than a C or a Go or a Rust developer. So we try to build a tool that abstracts away all of those details and allow you to just, create, build, so compile to Wasm, and then test and push your components in a couple of commands. I have a short video of that as well, if it works, just to show you the experience. You can create a new component. Let's pick Python. So it initializes all the code for you, all the width, all the WASI, all the WebAssembly, and it's pretty transparent. And then you can go and build it. So it compiles it using the commands that I showed you earlier with componentized BI. And then it's testing it. It's actually raising a not implemented error because it's Python and I didn't implement anything. But you get the stack trace, you can go and debug and do all this stuff. And then you can push your component to a registry, and that automatically appears and can run on top of all the hundreds of edge locations in our managed service. So that's how we allow third-party unsecure code to run, thanks to WebAssembly. I have a bit more details about this and where this stuff runs. Today it runs on partially at the edge directly, partially in the cloud. That's why cloud and edge are not mutually exclusive. And some of the stuff runs on top of AWS Lambda, for example, because it's a very similar compute model. I also have the huge AWS diagram for the most curious of you, and maybe we can look at it later if there are questions about how this stuff actually works. But there are a lot of different components, and the data sits in a lot of different places, from Fastly to Google BigQuery to AWS Lambda and some of the AWS API and some of the other SaaS third-party integration like Stripe. I don't have more time to dive deeper. Sorry, guys. So these are my takeaways. CDNs, if you didn't know yet, are not just about caching and DDoS protection. You can actually build applications on top of their compute platforms. And that's how the edge enables you to build a kind of a new type of application, or extend existing application with new features that don't force you to change the client or the server code. I think WebAssembly and WASI together have a lot of potential, not only for the Python community, but also to build this new cross-language kind of portable community. We're trying to build our own community of components and developer and open source developer that push some of the stuff to the registry. And most of the things I talk about on the edge side are also open source on GitHub for you to explore. So thank you for joining, and let's connect on LinkedIn if you're curious. Do we have any questions?
Question for you. From an architectural point of view, what are the basic knowledge to apply WebAssembly?
The basic knowledge to apply WebAssembly from a technical.
Yes.
I think it's important to understand what you want to support, and because there are already many predefined interfaces like HTTP endpoints or CLI kind of use cases, you need to understand if you can reuse those or if you need to build your own WASI interface to support a specific use case. What we did here is to create our own domain-specific interface. We are not using any of the pre-built WASI interfaces ourselves. But then architecturally, there are some latency and compatibility things to keep in mind. The host can run as many components as you need, and the component itself is self-contained. If you don't give access to file system and operating system, it's not going to get access to it. But if you do, you need to be aware of how and which folders or which, how do you control from the host point of view access to those interfaces. There are some differences in the languages that you can support. We took the decision of supporting all the possible component model languages, from the C to the Python and the TypeScript and the Rust and so on. But if you really need speed, sometimes you really need to stay focused on the compile languages. It really depends on what you're trying to do. I think it's incredibly powerful, the idea. And some of the other companies that you probably know, like, I don't know, Shopify. If you look at Shopify, they support like website customization, and they're using, WebAssembly behind the scenes. You just give them the code and they compile it for you into WebAssembly component. It's really powerful for extensibility of your platform. And so, yeah, maybe let's dive deeper together if you have more questions about architecture. Any other question?
Thank you. Yes. How does it work if your Python code is built over binary libraries like NumPy?
Good question, especially on the edge. For example, I mentioned Cloudflare, and Cloudflare workers have support for Python in beta, but they only support the standard library, which is a huge limitation, right? But for good reasons. I think for the general use cases not related to edge computing, it's still a bit of a pain because in the end, everything that you build, everything that you compile needs to be part of the big WASM file. I haven't tried myself. I think there are ways to compile the scientific library and libraries and NumPy and SciPy into WebAssembly, and that's how some of the notebooks in the browser stuff is happening. We don't do it ourselves because we don't need that kind of stuff, but I think it's entirely possible.
Thank you.
Cool.
Another one.
Thank you. Let's go.
Do you think that common logic or business rules could be shared in a WASM module in a company tech stack in order to be used in different environments or runtimes?
I think so. I think that's one of the use cases, the idea that you can build, you can almost think of it as a microservices kind of thing, where each microservice is a little component that's stateless and that does one thing with a specific interface. What WebAssembly gives you is that instead of just using HTTP as an interface, it gives you code generation and specific types so that the entire thing is already built for you and you don't need to enable network connections to communicate between the services. So that could be a cool use case. If you have that use case, come talk to me. I would like to learn more.
Okay. So thank you, everybody. Thank you, Alex, again.
Thank you, everybody.